Okay, so today is a snow day, so in lieu of an in-class discussion, we're going to do some other things. So I've got several announcements to make. These were all also made in the email that I sent out to you, but just to recap, um, instead of having class today, um, you should still have read the PDF on nuclear. It's posted to Moodle. We're reading that in lieu of reading Wolfson this for the nuclear module. And we are going to watch I guess the next one is that you're going to watch this, which you have apparently already found. So we're going to just finish up the lecturing that we started last week on kind of basic overview of what nuclear energy is. And finally, next we will watch the PBS Nova special, the nuclear option. So that's linked in this PowerPoint and also on the Moodle site. And there's some questions that I wrote as I watched it. So all those questions should just be in order and they should be pretty straightforward to answer. It's more just a did you watch it kind of reading quiz grade. So that should be a good way to get 100% on a reading quiz. And that video is about 50 minutes, and it's a sort of 6-year follow-up on the Fukushima disaster and what went wrong there and where the future of nuclear energy will be. And then next week we were supposed to start renewables, so we're going to start talking about them this week. So that's another video PowerPoint that's posted to Moodle. And you can choose to watch that now, or you can choose to watch that sort of sometime before you come to class next week. Okay, to continue with our announcements, we're going to have only one more module quiz. So we had originally planned on having two, one for nuclear and one for renewables, and I'm just going to combine them into one. It just doesn't make that much sense to set them into separate tests since we're sort of covering them simultaneously thanks to the way that the snow day is affecting us. So that will be our second to last meetup on April 12th, and I will make it be worth 2 module quizzes worth of material. So next time when you see me, that will be next Wednesday, and please, we're going to be doing the things that we had planned on doing in class today. So that is the EPA's fracking report. We'll do a class discussion on that. And there's a reading assignment to turn in, which you have, some of you certainly have already done. And if you haven't, you have another week to do it. And then we will also have the debate on the Indian PowerPoint and the Indian power plant and all the details about that we talked about just before spring break. If you don't remember your group, that's listed on the Moodle page. And we will also have a reading quiz next time you come. That's going to be on portions of chapters 9 and 10. Rather than making you read the whole of those 2 chapters, there's sort of a bunch of little bits that you need to read. Those are the chapters on renewable energy in your textbook. Finally, last but not least, last time I saw you, I passed out our first essay. So that's the essay about living downwind of a power plant, and would you rather it be a natural gas, a coal, or a nuclear plant? So I guess that's probably 2 weeks, the draft is due, so that is optional. If you want details from me about grading, you want to make sure that you get the grade that you want to get, turn in that draft and I'll give you back comments a few days after you turn it in. If not, the final draft for everyone is due April 5th. So let's talk about what we did last time. So we talked about nuclear. So we started out in the very beginning and talked about atoms, and they're made of protons, neutrons, and electrons. And we also introduced the idea of an isotope being an element that has the same number of protons in its nucleus, but different numbers of neutrons in its nucleus. And following up on that, we also introduced the idea of 2 different types of radiation. So from And at the very beginning of this class, I think we're comfortable with the idea that not all radiation is bad. You emit radiation, I emit radiation. Everything that has a temperature, so that would be everything that exists in the universe, emits some kind of radiation. The stuff that is not bad, we're calling non-ionizing radiation. And the stuff that is potentially bad is the ionizing radiation. So we use it for medical x-rays. It's also what is emitted when nuclear reactions are going on. So what we use as the dividing line between these two different types of radiation is whether or not a single photon or a single little bit of ionizing radiation carries enough energy to strip an electron from a molecule. If it can do that, then it can damage you. All right, so atoms are made up of protons, neutrons, and electrons. And inside their nucleus, they have protons and neutrons. And isotopes come into play because isotopes are atoms of elements that have the same number of protons in them, but they can have different numbers of neutrons. And depending on how many neutrons they have, they can be a stable atom or an unstable atom. In the case of unstable atoms, there will be unstable things like to make themselves stable. So they're going to make them more stable by releasing some radiation. And when that happens, that is ionizing radiation. And when all of these things happen together, we call that a radioactive element. So last time we tested a bunch of different radioactive materials, and I mentioned that most of your smoke detectors contain a radioactive element. And we shouldn't be super concerned about the possibility of getting exposed to little bits of radiation because we are exposed to radiation every day, whether you like it or not. So on average, you are exposed to 6.2 millisieverts of radiation every year. We did a little online calculator last time where you calculated your individual dose, which varies considerably because you may or may not have had a lot of medical procedures last year. My radiation dose is heavily focused on the fact that I do a lot of cross-country flights, so I get a lot of radiation just being high up in the atmosphere on airplanes. And so we are constantly being exposed to not just the harmless kinds of radiation, but also the harmful kinds of radiation. Okay, so what is the fuel at a nuclear power plant? Nuclear power plants use uranium, and I showed you a picture of, or not a picture, I had a little rock that is uranium ore. So uranium comes out from a rock like that. And in order to turn the rock into something that is useful, we have to do a process called enriching that uranium. So that is where we take uranium, which is naturally has about 1% of uranium-235. So that's the type of uranium that we need for nuclear reactors. We have to enrich it all the way up to about 4% uranium-235. Once we've enriched the uranium, we form it into small fuel pellets. We stack it into fuel rods and group them into fuel assemblies, and we pop them in the power plants. One fuel assembly makes its way into the power plant and stays there for about 3 years. And there's some photographs of those. So on the left is the fuel pellet, in the middle is the fuel rod, and on the right is a photograph of what the fuel assemblies look like. So we send those things to the power plant and we pop them in, and something called fission occurs inside the power plant. Fission is the process of neutrons striking unstable uranium-235 atoms. Those unstable uranium-235 atoms split, and that process of splitting releases a lot of energy in the form of heat, and it also releases a few additional neutrons. we call that split fission. And I think one very strong appeal of nuclear energy is the amount of waste that is produced. While the waste is definitely radioactive and not waste that you want to have any interaction with, it's not very much of it. So one uranium fuel pellet has the energy equivalent of 3 barrels of oil, a ton of coal, 2.3 tons of wood, and 408 cubic meters of natural gas. So we are talking about things that are easy to ship, easy to contain, and things like that. Okay, and then we also talked some about how a nuclear power plant works. So a nuclear reactor is, in almost all cases, just a water heater, just like every other power plant that we've ever had is a water heater. All right, so at a coal plant, we burn coal to make heat, and that heat goes on to turn a turbine, etc., etc. The same exact thing is going on at a power plant, except for the way that we produce the heat is through fission and not through burning coal or gas. So this is a photograph of a typical nuclear power plant, and that big chimney is steam coming out of there. So the only thing that is actually emitted from a nuclear power plant is water vapor. So in normal operations, nuclear is by far the cleanest thing the cleanest way that we get large-scale electricity. This is a diagram of a pressurized water reactor, which is a very common type of reactor that exists. And I wanted to show this at the time, and I'll show it again to point out a couple of things about it. One is that, as I said previously, this looks a whole lot like a natural gas or a coal plant. We have cold water coming in and being heated. That cold water leaves, and it's very hot steam when it leaves, and it turns a turbine, which goes into a generator. And then after the turbine, we have some very hot steam that needs to be cooled before it can sort of repeat the process again. Another thing worth pointing out here is that all of the fission goes on inside that containment building. And that containment building is a 1+ meter, so 3 or 4 feet thick, steel reinforced concrete chamber that shields out any radiation from escaping from it. And what is not present in that was present in our coal and gas plants is a smokestack. So no emissions other than water vapor are coming out of this plant. So the lack of emissions does not mean that there is no waste produced. So like all industries, power plants do produce waste. And a typical plant produces about 30 tons of used fuel per year. That may seem like a big number, but that is tiny in comparison to what a coal plant produces even in a day. So we call that used up fuel, the waste product produced by a nuclear power plant. We call that spent fuel. And there you go. So you have about 1,000 times more coal waste produced in a coal plant. And a quote that I like here is that if all the electricity used in your lifetime came from a nuclear reaction, that waste would fit into the size of a soda can. So we are talking about very different scales. And inside so there's 2 steps that happen when the waste leaves the power plant. The first step is that fuel assemblies go straight into a pool called the spent fuel pool. And it spends a few years there. And over those few years, up to sort of 80 or 90% of its radioactivity decays away into the spent fuel pool. But spent fuel has to be isolated not for just a few years, but thousands of years, probably about 10,000 years before it's considered totally safe. So after it goes to the spent fuel pool, we have to take it somewhere, and the next place that we put it is in a dry cask. And that is pretty much the end of it for us right now. So it goes into these dry casks. So these are steel reinforced concrete bins, and the vast majority of nuclear waste is still stored on site at the nuclear power plant. In the US, we had planned on storing it somewhere underground in a geologic repository, but Yucca Mountain, which is a mountain in Nevada, had originally been the plan for that, but it became politically not very popular, and we stopped working on that. So we really don't have any long-term storage option for nuclear waste. And that was a very long review to the things that we talked about last week. But it was 2 weeks ago, so I guess it was worth spending some time on. So the last thing that we need to talk about is the concerns surrounding nuclear power. And the main concern that we have is it safe? Okay, so while the fuel is very small in volume, the waste is very radioactive. And you want to make sure that waste doesn't have any interaction with the environment. And you also want to make sure that in the case of a meltdown or an accident, that waste doesn't actually end up melting down and exposing people nearby. So there's a lot of things that are in control set in place to improve nuclear power plant safety. So some of those features involve using laws of physics and natural properties of material. So this is, for example, the containment building, that 3 to 4 foot thick steel reinforced concrete chamber that the nuclear fission occurs in. Another thing is that you have safety systems that have many backups, right? You don't want to be in a situation where if the power goes out, you could have a nuclear meltdown. So you need to make sure that you have backups and backups to those backups. You also want to use strong barriers, such as the containment building, that will keep radiation inside if all else fails. And another thing is that you need to have a really well-trained staff that know how to behave in emergencies and that run emergency simulations routinely. So to follow up a little bit on that first point again, it's actually pretty difficult to get a chain reaction going and then to keep it going. All things have to be just right for that to happen. So the fuel and the coolant and the chain reaction process itself guard against some of these accidents. So I showed you a little video last time of some people who set up mouse traps, hundreds of mouse traps with ping pong balls on them, and we sort of visualized that the mouse traps were all like a uranium atom, and they had a single ping pong ball as a neutron to shoot out in their reaction. And if those mouse traps are hit by a ping pong ball, then they will snap and shoot another ping pong ball out into the air. And you can imagine a situation where if those mouse traps were too far apart, they wouldn't all snap. So that's sort of analogous to this chain reaction, right? If the fission products, the enriched uranium, is too far apart, then the chain reaction won't keep going. There is a picture of what a containment building wall looks like. So you can imagine even explosions that can happen inside the containment building will still be contained by that concrete wall. They are also designed to address emergencies. So we design power plants to have multiple backup safety systems, and also that they should be strong enough to survive things like hurricanes or terrorist attacks, earthquakes, tsunamis, etc. And The Nuclear Regulatory Commission, the NRC, regularly comes in and investigates safety checks in all the new operating nuclear power plants in the US. So we have multiple backups in place and lots of safety checks that are going on, lots of safety inspections that are going on to ensure that things are operating as smoothly as possible. And anything that could be dangerous is caught long before it becomes a problem. Okay, so the NRC, the Nuclear Regulatory Commission, comes in all the time, and they license and they inspect construction of new plants, and they regulate old plants and run safety checks on old plants. So I just want to point out that it's not dangerous living near a nuclear power plant. The only reason that we're concerned about being near nuclear power plants is because they are dangerous in the event of a meltdown. So these are your typical exposure is about 620 millirem, MREM. That's 6.2 millisieverts per year. And living next to a power plant exposes you to 0.5 millirems, basically less than what you're exposed to every year just having a television in your house. So normal operations of a power plant are really nothing to be concerned about. They release virtually no radiation. That's actually quite a bit less radiation than is emitted during normal operations of a coal plant. And the emissions that they put out have no sulfur, have none of those pollutants that we were talking about when we were talking about environmental impacts of fossil fuels. All that they do is tiny bits of radiation, and which are so small that they're kind of almost not worth measuring, and water vapor. So, we have some ways. This is those dry casks are actually meant to not be stored on site at the power plant indefinitely as they are. They're designed to be able to be put on a train or any other sort of fast-moving object and be able to withstand really large collisions. So this is some pictures of a crash test video, and if you are interested, you can click on that YouTube link on the PowerPoint and see a video of the crash test that they did back in the 70s, where they strapped these things onto moving trains and collided them at very high speeds and sort of verified that these dry casks are built for huge collisions and huge catastrophic accidents. So that is all great, but if this was the whole story, then we would have a lot more nuclear energy than we do right now. The reason that people are concerned about nuclear energy is because even with the best safety protocols, accidents do happen. And we have had 3, I would say, kind of prominent nuclear accidents in the world since we started getting electricity from fission. I'm going to talk about the 3 very briefly and in order. So 3 Mile Island was when happened in Pennsylvania near us. Actually, this power plant is still in operation. So this was in 1979, where there was coolant that was lost, and water is used to cool the reactions, and so things got very hot, and that released a lot of radiation into the containment building. But you remember the containment building was this large building that's concrete surrounded, so there was virtually no radiation that was actually emitted to the surrounding areas from this. So this was a really hyped up event in the US. It was the first kind of real event that could have happened, and I think it got blown out of proportion probably because of that, but there were no serious injuries or death. The average amount of exposure that a person got was tiny, but it really alerted us to a lot of fears about radiation poisoning. And it was a big setback in that way. In contrast to 3 Mile Island, Chernobyl was a real nuclear disaster. So this happened about 7 years later in 1986 in Chernobyl, a power plant in Ukraine. And it actually happened during a routine space safety check. They turned some things off and some things didn't turn back on properly. And as a consequence of this, lots of radiation was emitted. So 28 workers died on site. Of the about 600 workers that were there, about 28 of them died on site. And there was no containment building at this reactor, so there was nothing to prevent that radiation from being emitted into the surrounding areas. So a couple of statistics are that of those 600 initially workers, 134 had acute radiation sickness from their high doses, and 28 of them eventually ended up dying. And they estimate that about 4,000 cases of thyroid cancer have resulted from this, but really radiation was spread all over Western Europe and Eastern Russia, and of course Ukraine. This was a big deal. This was in the Soviet era, so when the initial meltdown occurred, there was really poor communication about this. The initial reaction was to try to cover it up rather than to alert the people that lived nearby that they needed to evacuate, and that made things a lot worse. But this is by far the worst nuclear accident that we've ever had, and it was entirely preventable. We don't have any nuclear reactors anymore that don't have containment buildings. That's a bare minimum, and even the presence of a containment building would have made this a much better scenario. So that was 1986, and fast forward 25 years, and we really didn't have any nuclear accidents to speak of. There's sort of constantly little radiation leaks that occur, and those are kind of what you hope to find. There's little radiation leaks that are observed and fixed and dealt with, and it's not really a big deal. And so we'd been going for a long time without a real nuclear accident until 2011, when Fukushima occurred. So you're going to watch a whole long video about Fukushima, so I'm just going to kind of hit the main event, which is that there was an earthquake, a magnitude 7.9 earthquake that occurred right off the coast of Japan. And it initially happened the way that it should have happened. So the earthquake happened and the power plant lost power, but the backup generators came on and inserted those control rods into the nuclear reaction site. So that, remember, the control rods are these rods that absorb neutrons and prevent the nuclear chain reaction from being able to occur. And everything was going as it should. But as often does happen with earthquakes over the ocean, there was a tsunami that was triggered. So that tsunami washed over the Fukushima power plant, which is right on the coast, and that took out their backup generators. This was a big deal because while the nuclear chain reaction is controlled by those control rods, there is still extremely hot radioactive material inside the containment building. And this was a water reactor that is cooled by water, and it needs to have water constantly cycling through it for a period of a few days in order to cool everything down. And without the backup generators to pump that water over things that were going on inside the containment building, things got very hot and kind of caused our meltdown. So it's in contrast to, I think, the Fukushima or the Chernobyl accident. This was very well publicized, very well broadcast. Evacuations happened very quickly. There are currently no deaths that are attributable to radiation release from Fukushima. In contrast, there's about 18,000 deaths associated with the earthquake and the tsunami in this area. So, and in the future, because as you know, sort of radiation is something that we worry about over the long term. Estimates of how many people might die as a result of their exposure range from none up to hundreds. And I think when you go into the hundreds, you're talking about the people, the workers that were there on site and that are still there on site being exposed to high levels of radiation. So what you're going to watch is a documentary called The Nuclear Option, which I described earlier. So there's the link to it. That link is also posted on Moodle. And in New York, we are a big nuclear energy state. So we currently have 6 operating nuclear energy sources in New York, 2 at Indian Point, that's downstate. And if you have begun preparing for your Indian Point debate, then you probably know quite a bit about Indian Point at this point. We also have 4 more upstate. And we currently get 34% of our electricity from nuclear. That's quite a bit higher than the US average. But a full 40% of that comes from Indian Point. So 10% of our electricity needs in the state come from Indian Point. And we just announced in the last few months that we're going to be decommissioning Indian Point. So what we're going to do to replace that 10% is kind of up for debate and up in the air. And that is the end of everything that I wanted to talk about having to do with nuclear. So I'm going to go upload this online so that you have something to watch tonight. And I will, I guess, see you in a little bit talking about renewables.